So the next topic is sensitivity analysis. So after we have the optimal solution and maximize or minimize objective function, what if some of the parameters are changed? What does that affect our objective values? How does that affect our optimal solutions? So that's kind of sensitivity analysis. So by using the report, we can also have we can do the sensitivity analysis. So, for example, we still consider the minimization problem that we used earlier. So we need to produce two types of products. We have objective function, we have constraints. So if we go back there, the model, and we go to the sensitivity report, we can see we have some shadow price and so on and so forth. What I mean, so the shadow price for constraint is the change in the optimal objective value if the right hand side of the constraint is increased by 1. So for the non-binding constraints, so they always have 0 as the shadow price. So if we go back there, so the non-binding result, it should be sensitivity value. So here, product A provided, so the final value, so the actual value for as the optimal solution is 250, and the minimum requirement is 125 and it's not binding, and the shadow value is 0. That means even if I increase this 125 by 1, which means I make it by 126, it doesn't change the objective function value because I already have 250 gallons produced. Because increasing the minimum requirement does not affect my decisions because I already produce way more gallons than your minimum requirement. So that's why the shadow value price is 0. But if we talk about the total production provided, it is a binding constraint, so the shadow value is 4. That means if the requirement is increased by 1, the objective function value will be increased by 1. Okay, and if we go back, and the shadow values are symmetric. The negative of the shadow price is a change in the objective function for decrease of 1 in the right hand side. That's if we go back here, because the processing time is less than or equal to. So the value here we see is a negative value. So that's a shadow price. Okay, we have the screenshot. And the next one is the reduced cost. So we have this kind of analysis for decision variable. So the reduced cost for decision variable is the shadow price of the non-negativity constraint for the variable. And allowable increase and allowable decrease indicate the change in the objective function coefficient for which the current optimal solution will remain optimal. So how much I can change the parameter such that the objective function or the optimal solutions will remain the same. So how much flexibility do I have in terms of the changing the coefficients of the decision variables? Okay. So that's what we need to know about sensitivity analysis. So that's the one. The next one will be some general cases. So far, when we were talking about the previous two examples, we use A, B, S, and D to define the decision variables. For general purposes, we use variable X to denote the random variable, or the decision variables. So instead of use S, let's use X1 to denote the first decision variable, number of standard bags, and use X2 to denote number of deluxe bags. Okay. And one disadvantage is that we can, if we use X1 and X2, you cannot easily tell what this decision variable means. If you use S, you know, okay, this is about the standard max. But if you use general term, we don't know what that means. So if we use a general term, this is the model will look like. We still have the objective function and the constraints and so on and so forth. We are just using different notations. And we have some examples. I will skip this investment portfolio example. Let's go to, I think I want to talk, yes, the translation problem, because we want to use this problem in the next topic. So this is one of the applications. So translation problem, planning problem. So we have a set of supply locations. We have another set of demand locations. And here we want to decide how many goods we need to ship from each of the supply location to each of the demand locations. And our objective is to minimize the shipping cost. So that's the false generator. So if we open the file, so this is the file, but I want to give more information about that. So for the origins or supply locations, we have 3 of them. So each location has the capacity. So the number of units to be shipped from each of the location cannot exceed the production capacity. So that's the supply side. Demand side, we have 4 demand points. All of them have their demand. So that's the supply and demand. So if we want to plot this relationship, we want to know how many units I should ship from Cleveland to Boston or Chicago and so on and so forth, and we do this to all the locations. Okay, so now let's model our problem. So our objective is to determine the routes to be used and quantity to be shipped for each route, and our objective is to minimize the transportation cost. And let's use the Xij to denote the number of units to be shipped from supply point I to demand point J. Then here's our some cost parameters. So that means if I want to ship 1 unit of goods from Cleveland to Boston, so you're gonna that's gonna cost $3. So the same thing for other combinations of supply and demand points. So that is how we model the constraints, the supply constraints. The number of units to be shipped from each of the supply location cannot be greater than the capacity. And the demand, we have to satisfy all the demands. So the number of units received from each of the location has to be exactly the same as the demand for each of the location. So that's the constraints. Our objective function here is the objective function. We want to minimize the total transportation cost, and we have constraints, and of course all the decision variables have to be non-negative. Then we are going to solve this problem in Excel. So we are going to use the solver, objective function cost, decision variables. So those are our decision variables, and then we have a set of constraints. So we have to make sure all the demands are satisfied, and we have to make sure that the supply, the number of units to be shipped does not exceed the supply. And then we can solve the problem and get the optimal solutions. Okay, so that's one of the applications. The next one I'm gonna skip. So if you're interested, I will upload the Excel files and you can play with other examples. Okay. And the next topic is to determine the optimal, the alternative optimal solutions. I will talk about that in the next video.